Okay. Good evening, everyone. Yeah, let me get started. See, normally when I do for my software verification course, when I discuss Hoare logic, I introduce it in a formal way, just like I introduced propositional logic and first order predicate logic with its uh, syntax for the formula and the meanings and so on. This time I thought I'd try a little bit different. So that's why I started with kind of an informal way of introducing by using the example of a DNN and making it look like a program and gradually introducing the concepts. Okay, now I don't know how well it has worked. So I'm going, not exactly going back, but today I will introduce Hoare logic in a formal way, and then move on to discussing the one topic that is quite important, which is how exactly loops ought to be handled when you have loops in program. Okay, so I will be, like I said in my email note, I'll be asking questions so that I want to make it interactive to make sure that you guys are understanding the important stuff. Yeah, so to summarize what we did in the last time, like I said, we used DNN as a program to informally introduce elements of program verification for straight line programs so far, starting with pre and post as a specification for program. Then when we introduced concepts of strongest post condition, weakest precondition as two ways to express the effect, that is the semantics of executing primitive commands in a program. Then when I showed you how they can be composed to verify that the program satisfies the pre and post condition. There are two ways of doing it. One is in a forward direction by propagating the strongest post condition, starting from the entry point to the exit point, by repeatedly calculating the strongest post condition for each statement in your program. Or you could do it in a backward way by calculating the weakest precondition starting from the post condition and pushing it all the way to the entry point, and then checking if your precondition implied the weakest precondition at the entry point. We also noted that the conjunction of the individual strongest post conditions after each command can be considered as a logical model of the entire straight line program. And that was indeed the basis for this encoding, which is called single static assignment, which uses time-stamped logical variables encoding as an encoding of a combined behavior for straight line programs. All these things that I introduce are elements and part and parcel of this logic introduced by Hoare for proving correctness of programs. Today I'll be kind of introducing it in a formal way and move to discussing how to verify programs with loops. Okay, so that is the idea. Okay, so just to make it concrete, I mean, because this is whole logic is meant for verifying programs written in a particular programming language. I'm introducing a very a small toy programming language, which has these commands: a skip command, an assignment statement, and sequential composition of two, commands, and an if-then else conditional statement, and a simple while loop to write loops. Okay, and we assume that the program uses a finite number of variables drawn from the set V. Expression is any expression, using the standard operators, and I haven't specified the operators as part of the syntax. And beta, there are two kinds of expressions: Boolean expression and a non-Boolean expression, giving values for some unspecified domain, okay, which is unimportant for the purpose of this logic at this time. Okay, this you already know, so we have already introduced. Post condition is, the state, final state that is expected to be true at the exit point of your program. Precondition is the assumption that is made on the state. That is, whenever I say state, I hope you know it is just evaluation for all the variables in the program. So this is a condition on the start state, that is at the entry point. Now, for us, at least for now, verification means if you start the program in any state that satisfies a precondition, after executing the program, when it terminates at the end, at the exit point, that the post condition has to be true. Of course, this is what is traditionally defined as program verification, but this is what is called correctness of program to be verified. But these may not be the only things that we want to prove, because there's so many other things that are of interest as well. But that is not addressed by whole logic. Okay, but there are techniques to prove them as well. For example, you may want to show that the program executes within a certain time, and using certain resources in terms of memory and so on. Now, right now we're restricting ourselves to sequential program. There is this aspect of concurrency, and we want to show that every possible ways of scheduling instructions in a parallel, in a concurrent program produces the same results. And more things like responsiveness, something always happens, eventually happens, and so on and so forth. Okay. So, but that itself, I mean, the flavor of that I gave you in terms of how the specification itself can be, quite complicated. But for now, we discuss program verification in terms of proving pre and post condition for sequential programs. Okay, I'm going to skip these things. Okay. So there are two notions of correctness that one can view. One is partial correctness. One cares about. Okay, partial correctness. So that addresses this question. For every sigma that satisfies, for every evaluation, for every state, okay, for every evaluation of the program variables that satisfies the precondition, if the program terminates with some state sigma prime, then sigma prime satisfies the post condition. So the partial correctness does not care about termination, okay? It checks if ever the program terminates, then it has to satisfy the post condition. A total correctness case includes termination as well. That for every sigma that satisfies the precondition, the program must terminate, And when it terminates with some sigma prime state, the post state, must satisfy the post condition. For now, I will introduce Hoare logic and its components as it is sufficient to prove partial correctness. Okay, maybe sometime later on, as we may address total correctness. Okay, these are some historical notes as to when this logic was proposed and so on. Okay, it is it was done by two people around late 60s. Okay, the basic judgment that whole logic is built on, and it means to define is this what is called a Hoare triple. Okay, I've been kind of mentioning it informally, but it is written this way. That is, here Q is a program, P and R are formulas written in uh, just a moment. Yeah. Yeah. So this is actually a atomic formula in Hoare logic. As I said, P and R are expressed in general in first order predicate logic. P is the precondition, R is the postcondition, Q is a piece of program, a code. Okay, and this holds, it is true if the assertion P is true before initiation of program Q, then the assertion will be true on its completion. Okay, that's when this Hoare triple will be true. That is, more formally, for every x and y, such that here x's can be a vector because they can be it's not a single variable, it can be the predicate p can be defined over any or all of the variables used in the program. So if px is true for every x such that px is true, and when the program q is executed and terminates on x producing output y, then it should be such that R must be true on y. That's what this thing means. Note that if P, the predicate itself, is false, this is vacuously true. Okay. So it only cares about those inputs for which P is true. That's the what the Hoare triple means. Okay. Now, given this understanding, uh, for example, if x is equal to x plus 1, if you start in a state where x is greater than or equal to 0, since x is incremented, x has to be greater than 0 as well. So this is obviously true. Are there my question to someone, so who is, let me pick someone who all are here. Okay. 1, 2, 3, 4, 5, 6. Okay. I'll go in that order. Ritra, Bijin, Deep. Okay. So my first question is, what are some other, hello?
Can you repeat the question? Like I
Yeah, yeah,
missed
yeah.
a part.
No, I'm still starting the
Oh,
question. Okay.
okay.
So, so does everyone agree that that when you start with x greater than or equal to 0, and after the assignment, x greater than 0 will hold good. Okay.
Yeah,
Yeah.
definitely.
My question is, what are some other possible post conditions for which this triple can still hold?
Greater than equal to 0 will also work. X greater than equal to -1 will also work.
Correct.
X,
Okay.
X
So
greater than equal
x,
to minus.
yeah, yes. If x greater than or equal to minus, okay, and of course, the post predicate true, it is where it says, oh, the values, the x can be anything, may also hold good. Correct? Okay. So that is why. So this, in some sense, so there are several candidate, P and Q for which the Hoare triples can be valid. Now, just like that's why there was this concept of strongest post condition. Okay, in some sense, x greater than 0 represents the something that the strongest that you could state about the execution, the effect of executing x is equal to x plus 1. Okay. So if you are able to, compute the strongest post condition, then you may be able to verify uh, any post condition that you expect to be true. So that is the motivation for coming up with having a version where you can get the strongest post condition. Okay. And here in this case, the weakest post condition, as I said, is true. Okay, because true, these predicates are said to be strong and weak in terms of the number of values for which that thing is true. So if a true is also, because it includes everything, all possible values, that's the weakest predicate for which this whole triple will be, true. Okay. Now, skip in that language that I introduced is, meant to do is a no-op kind of a statement. So, let me go to the next person, So if, is this, I've given out the answer, this is not true. Okay. Why? Um in Bijayan, answer if he's still.
Sir, he wrote that he is in the library, so he might
Oh,
not
so
be
he
able
won't be
to
able
answer.
to speak out. Okay, so let me then go to Deep Pro. Who was the first person who answers the last one? Was it Aritra?
Yeah, I was audible.
Okay, so I'll go to Deep Pro. Deep Pro, are you there? Hello. Well, then let me go to Vardhan.
Oh, actually, Vijayan is writing that he might be able to answer the question in the chat. So,
Okay.
it's good.
Hello, should I answer or Vijayan wants to answer it?
I'll get uh, I'll give Vijayan another chance. So why don't you, Deep Pro, if you're there, go ahead and answer. Please go ahead, Deep Pro. Oh, Dipro is not responding. Okay, then Vardhan, you can go ahead.
Yes, so if we see the form like PQR form, so the statement says if P is true before the initialization of the program, then Q should also be true. But this is not true here because like it's not directly implied. Like if X is greater than 0 in the beginning before the beginning of the program, which is skip here, it does not imply like Y would also be greater than 0. There's no connection. I think that's the reason.
Um, well, remember the skip does not change. I mean, it doesn't update the value.
Yes.
Yeah, you're right. And a clear way of saying is you don't know what, in the precondition is not constraining Y in any way. So Y could be anything in the pre-state, okay? In particular, Y could be negative, for example, okay? It could be negative. Since skip does not change the value, if you start in a state in which Y is negative, okay, then Y could not be greater than zero in after you execute skip, because skip does not change anything. Y will retain the same value as before, which could be negative, right? So therefore, this is not true. Okay. Since skip itself does not change. Okay, I guess that is kind of what you implied. Is that clear? Yeah.
Yes.
Okay. Now, here, okay, so you're starting in a precondition in which you're not constraining values of any of the variables. That's what true means, okay? Then if you do if x is greater than y, then yeah, then if you execute this statement, okay, then the question is what is the strongest post condition that you could state. So if x is greater than y, y is assigned to x, therefore x will be equal to y. Else you're retaining the same thing, okay? Else means x is less than or equal to y. So if x is greater than y in the pre-state, then you're making x and y be the same. So x is equal to y. Otherwise, it'll remain as before. Okay, which that's the case where you're executing a skip, which is x is less than or equal to y. So when you put these two, the result of executing the two arms together, x will be, you can conclude that x will be less than or equal to y. Is always guaranteed that x is less than or equal to y. And that's what, so that is the strongest thing that you can actually state, okay? Similarly, if x is greater than 0, here the question is, what program can ever make the post condition false? This is kind of a corner case, a tricky kind of situation, okay? Because false is there can be no value that can make false true at all, because false is always false. It is never true. Therefore, if you okay, so this can be satisfied only by a non-terminating program, because if it ever terminates, the program terminates, it has to terminate in some state where the variables take some value, but that value can never be satisfy the post condition. Therefore, the way the partial correctness is defined, this can be true of only non-terminating programs. Okay. Similarly, if you start with a precondition that is false, here the question is what should be the post condition? Okay. Okay, so let me now go give who else? Why is this? Oh, Bijan is asking why can't we write x less than 0 in order to get that? Why can't we? Okay, I'm going back to 4. Bijan is asking why can't we write x less than 0? What does that mean? I like x. Bijan, but the way that you wrote the whole triple, x less than 0 is not a valid program. A program has to be something that is a command in the program. Okay. So remember that in the whole triple, it's the pre and the post condition which are formulas in the logic. They are logical formulas. Whereas what is in the middle is a program. Okay. I know what you kind of implied. So you are now, x less than zero is not exactly a program that changes the value of x. Okay. You're right that if yeah, so that's why you cannot do that. You will have to have some program. Yes, even in this case, it can be yeah. So here, even if x is less than zero is say allowed as a command in your program, which can be just checks and doesn't thing, but still it terminates, right? So if it terminates, then it will terminate in a state in which x is greater than zero. I mean, unless x less than zero sets makes x less than zero, as whenever it terminates, regardless, x will hold some value. Okay, so then it cannot satisfy false, and that's why those are the two reasons. Okay, now let me, Pranika, are you there? So why should uh, yeah, here I'm claiming that if you start from a state, a precondition, which is false, for any, P could be any program, then your post state could be any predicate. Okay, this is like a little bit of a tricky thing. Okay, it's, but can anyone take a crack at it? Why is this? Why does this whole triple hold for any predicate as a post condition?
Because the precondition is false, so uh, anything the input, like anything we can, like it's false. So okay, like if the false will all I'm not like mm, okay. So maybe I'll think about it.
No, I think that's why I already remember that. This is because it's the way a whole triple validity is defined. Okay. Look at the way that this is the validity of this, the definition of validity of a whole triple is implication, okay? Is logical implication. It states that if px is true and then you execute the program and if it terminates, then r should be true. So there are two ways in which this can be vacuously hold, okay? One is the case in which q never terminates, okay?
False.
Yeah, because logical implication is true the way classical logical implication. If the antecedent is false, it is trivially false. Okay. And how can, there are two ways in which this can be trivially false. One is either if the program does not terminate, okay, in which case, this can be true of any predicate, okay, even including false. That's what that earlier example showed. The other way in which this can be vacuously true is if P itself is false. That's if your precondition is false. Okay. And that's what is happening. And I think that's what you tried to state, Aritra. And, so because by definition, for a precondition being false, or when the program is non-terminating, the partial correctness way of defining a whole triple, it is vacuously true, and that's why it is true for any any predicate. Okay, is that clear? Yeah, Pranika. Yeah, I mean you have to ask questions, Pranika. For thing. Okay, so Pranika, now maybe you can take a crack at this, given that explanation, if you're comfortable. Why is this not true? Okay.
I'm not quite
Yeah.
sure, sir. I will think about it.
Okay. So okay, anybody else who wants to, let me see who else is there. Did we? Okay, I'll go back to Vardhan. Okay, can you explain to us?
Uh, Hello.
Yeah.
Hello. Hello.
Yes, I can hear you, Vardhan.
Yeah. Okay. For the yes. So for the sixth point.
Yes, go
Uh.
ahead.
s- okay. Okay. Skip means like it won't affect whatever was true
Mm-hmm.
before the beginning of the program and after, and it does not change anything. So as because the initial assertion is already true, the first
Mm-hmm.
P is already true, but this does not imply after the running of the program it is the assertion given at after the program, which is R, it's not true. That means that's where the answer is no, I guess.
Yeah.
I think I can't explain very properly, but yeah.
Okay. And the better way to explain is that skip is a terminating program, right? So a post, no state can satisfy false. Yeah. So if you true is a state in which what does true mean as a predicate? Okay. So this is where I was saying that in order to understand these things very clearly, you have to be very comfortable with uh, predicates representing states. What does true represent? Okay. A true is a predicate that is true of any value. So what this means is if I start with any value for the variables, okay, no constraint on the variables, and skip always terminates, which means and it does not change any of the value of any of the variables. So the post state, the strongest that you can state about the post state is it could be any state, okay? And but because skip terminates and no state can satisfy false, this can never be true. So whenever you have a post condition which is false, it can only be satisfied by a non-terminating program because in this case the state, the strongest post condition is actually true, okay, because you're starting with some state which can be anything, and skip does not change any of the values. Therefore, the thing is true, the strongest post condition. But in any case, false cannot be satisfied with anything, and therefore, since skip is terminating, this can never be true. That is what is the correct answer. Similarly, if your post condition is so weak that you don't care, anything could satisfy it. It doesn't matter, okay, what your precondition is. Okay, that's what this thing states. Okay, there are more examples here, and you could you could go over them, and maybe if you still have doubt, there will be maybe not this Friday like I mentioned, every Friday is a tutorial day, okay? And if there are doubts that you have, and those are meant for for you, for you to take help in getting any doubts about the lectures in that week, for you to get them clarified. And there'll be examples, and it'll be run by the TA, so feel free to attend them. Okay, so what does whole logic have? Okay, the whole logic, I mean, I introduced this simple program. So whole logic has a bunch of inference rules, some rules, okay? Remember how formulated we formally defined propositional logic and first order predicate logic. First was the syntax, and then we uh, gave the formula. So in this case, the only additional formula is the whole triple atomic formula that whole logic has. Now, the second component of logic, defining logic, is to define which formulas are true in that logic, and that is done by means of a set of rules. Okay, and that's what whole logic has. Okay, it has one rule for every command in the language, such so that using those rules, you will be able to define when a whole triple will be true for any program in that programming language, and that's how it is built. Okay, so we start with defining for skip. Okay, so skip
Excuse me.
is, yeah.
Yeah, actually, there is a question in the chat by Deepto. He's asking, can you explain again what does skip does? Does it only replicate the previous predicate? That's his
Yeah,
question.
let's see. So this will clarify that doubt. Skip is like a no-op statement. It does not change any of the values. It keeps every variable retain the same value as it had in the pre-state. Okay, in the post state. Okay, and that's why if P is true, if P is the precondition, then after executing skip, P will continue to hold. Okay, is that does that clarify, Vijayan? Oh, who asked that question?
Deepto.
Oh, oh, Deepro. Yeah, I mean, replicate is not what I would, yeah, I mean, yeah, it does not change any of the values. Therefore, for any particular, see, the way that logic defines is for any given predicate, pre-predicate, it defines the post predicate for which that will be true. And in most cases, it will do it in such a way that uh, it gives the strongest post predicate. If P is the precondition, since skip does not change, the strongest thing that you can say anything about the post is that P will, continue to hold. Okay, on that condition will continue to hold in the post state as well. Okay. Um, Okay, this we kind of already said. Okay, and an assignment rule, there are two ways of defining. Okay, that one is gives the defines it by giving it the weakest precondition. The other one gives by defining it the strongest postcondition. Okay, so X, for example, so here this is the backward way of defining it. If you had a predicate, okay, two things note about these inference rules. Okay, this is why I'm saying these rules are like calculating predicates, okay? So given some PC, it is being stated for an arbitrary predicate that appears either as the postcondition or the precondition. So what it is saying is, if you want P, the predicate P to be true of the for all the variables, as a post condition, after this assignment is executed, it is defining what the precondition, what the weakest precondition that can make this post condition to become true after executing x is equal to e. So what it is saying is, if P is to be true on the value of x, after it is assigned the value of E, P must already be true on that value in the pre-state. Because what does an assignment statement do? It evaluates E, the expression E, with the values of the variables in the pre-state. And that's what is, and X is updated to be that value in the post state. Therefore, if and none of the other variables change, okay, and therefore X is the only one that is updated. Given that meaning, which means that value E, since X takes the value of E, whatever E evaluates to, so if you replace in this definition of P, see, we are all assuming that P is defined by some formula which has one or more occurrences of X and other variables as well. So then that predicate ought to be true when you replace X in that formula defining P by E in the pre-state. Okay, and that includes this whatever value that is satisfied by this version of the predicate in which X is replaced. This X, E slash X, you should read it as X being every occurrence of X in the formula P is being replaced by the expression E. That's what it means. Okay. So that it better be true. So it is kind of backward. And yes, the reason that this is exactly the weakest in the sense any state valuation of the variables for which this predicate is satisfied will result in P of X being true in the post state because of these two reasons. Okay. And that's, yeah, this defines the weakest precondition. So, for example, if X is greater than 0, if you want X to be greater than 0 in the P state after X is assigned X plus 1, then X plus 1, which is the value that X takes, itself better be true in the pre-state, which is what it is saying. X plus 1 has to be greater than 0, which exactly means if X is greater than or equal to 0, as long as X is greater than or equal to 0, uh, in the pre state, uh, after this assignment, X is guaranteed to hold in the post state. This is one way of defining, which can be, yeah. The other way is to do it in a, okay, which is what, we did. So if you start from a predicate P, this rule, it defines the post condition. So it answers the question, if you start from a predicate, precondition P, and what would be the strongest thing that you can state after assigning some expression, the value of some expression E, which may involve X as well as other variables to X. So it should be, so this is the strongest thing that you can state. Okay, what is that saying? The post state must include every pre-state that satisfies P in which X is up and X is updated to the value of in which X and only X is updated to the value that is of E as the value that E evaluates to. Okay, with all the other values of the values of all the other variables being unchanged, and that's what this thing says. So E, for every V that value of X in the pre-state that satisfies P, okay, and then that'll continue to hold in the post-state, and X itself, the X and only X will be updated to the value of E, and that is why the strongest post condition can be stated in an existentially quantified way. Okay. So for example, I'll give you two examples. X, if you start with X is equal to 5, then what this is stating is when I instantiate this, the rule for this predicate, okay, the precondition here is X is equal to 5. So the postcondition is, it says there exists a V such that V is equal to 5 and X must be equal to V plus 1. So one way to, and what is this existential saying? In this case, V has to be exactly 5. So you can replace V, you can eliminate V in this existential formula by substituting 5. And therefore, when you do that, you will get X to be exactly to be 6. Okay. And that is one way you can eliminate. And then, okay, suppose the precondition is X is greater than or equal to Y. Okay. Then as when you instantiate this, it says for any value of X in the pre-state such that v is greater than or equal to y, okay, the post state, the only way in which the post state changes is that it'll be true of x, x is getting updated to v plus 1. Note that this existential quantification is true exactly for those values in which x gets the value v plus 1, where v is for each value that v can take in the pre-state, such that that predicate, which in this case is v greater than or equal to y. Uh, Another way to, okay, so here, if you want to eliminate the existential quantification, you can introduce what are called certain ghost variables. Okay, if you now introduce certain logical variables that denote the initial value, that's the values that the for each for every variable in the pre-state, and that's what x naught and y naught are. Okay, so as long as you make sure that x naught and y naught, these are logical variables denoting the values of the program variables in the pre-state, as long as you choose these things such that they don't clash with your the program variables in here. I'm saying that x, suppose x is x naught, some x naught, y is equal to some y naught, okay, and x is greater than or equal to y, which is the precondition. Then after you execute this, I can choose the value x naught itself for v and then substitute that in here, which is what I'm doing here. So y is equal to y naught and y remains the same. And now I'm plugging in x naught in place of v in this existential quantification. Therefore, I'll end up getting x naught being greater than equal to y, and I can then I introduce a new timestamp variable, because x1 is as thing x, which is x naught plus 1, and I'm saying x will take that updated value, the value of the expression e, which in this case is x plus 1, evaluated for x, whatever the value of x is in the initial state, which is x naught. Okay. And this is how, okay, this is exactly what the existential version of the post predicate is stating, okay. And this is a way to eliminate that existential variable, okay. And you can see when this condition, although it uses a lot more variables, this is where the time-stamped variables is coming from. It implies x greater than y, okay? So in a closed form notation, or if you want to eliminate these things, is equal, this implies actually x greater than y. And that's how it has, the most general way of stating it requires existential quantification, because you're stating it for any arbitrary predicate, okay? Uh, yeah. So is this, yes. I hope this is clear. Okay. What I'm saying is this is the strongest postcondition stated in terms of existential quantification. And if you introduce these time-stamped variables to denote the initial value and the thing, then you can actually eliminate that existential quantified variable and state it in this more elaborated fashion. Okay. And that is how the basis, the idea for defining SSA encoding takes advantage of. Okay. Okay, any questions here? Okay, now this I'm going to skip. Okay, this is something for you to, for people that require more example for them to understand thing. So these are exactly the same thing that I've stated. So this is the post condition in terms of existential quantification. And if you want to state it without the existential quantification, you can do that by introducing these are called ghost variables, okay, to denote explicitly the pre values, okay. And yeah, So what are the other things? Okay, so these are, the skip and the assignment statement are the only atomic commands. So these rules define the meaning of, it gives defines the whole triple. Okay, one by defining the weakest precondition and the other by defining the strongest postcondition. The rest of the rules of Hoare logic, they tell you how to construct the Hoare triples for larger programs from smaller programs. Okay, so they are for these program commands that are program constructors. Okay, one is sequential command. So this says that if Q, Q followed, this is a program which executes Q followed by S. If this whole tuple PQR is true, and starting from P, if you execute Q, suppose R is true, and if you start from R and then execute ST is true, then when you compose Q and S together in a sequential fashion, then if you start from P, then T ought to be true because this program execution consists of executing Q followed by S. Okay. This rule is what allowed us to propagate propagate the precondition across the program, the way I illustrated last time in the class, to propagate it all the way to the exit point by computing the strongest postcondition as per the forward assignment rule, and then you could and all the way to the exit point, or you could start with T and use the assignment rule, the backward assignment rule that computes the weakest precondition and propagate T across each statement in the program and come up with the weakest precondition that holds good at the entry point. And that's how this rule allows you to calculate and propagate these conditions. Finally, there are rules. Okay, once you propagate, if you forward propagate across the program, and then you get the strongest post condition, then you can use that to show that whatever post condition that you have proposed as part of the specification is true, is done. Yeah, if you know R, and then if P, I'm sorry, this is for backward propagation. If you're able to propagate R to P, and then if your precondition is P prime, and then if P prime, you can prove that P prime implies P, then you can conclude that this whole triple, if you start from P prime, our post condition will hold good. Similarly, if you do propagate it in the forward direction, then if you start from P and then you propagate to R, then, and if your actual post condition is R prime, which is different than R, and if you're able to prove R implies R prime, then you get this. And this is what we use there. After propagation, the forward propagation, you propagate it to the exit point and then show that the strongest post condition at the exit point is implies the actual post condition that for the entire program, or you propagate it backwards and then show that it is the actual precondition implies the weakest precondition propagated to the entry point. Okay.
Is it like we are weakening the post condition kind of thing? The
Say that
reverse,
again.
like are we kind of doing weakening the post condition?
Well, that is one way. Yes, you could say that you are weakening. If you see the advantage of uh, your hey, if when you compute, okay, one way you could say you're weakening the post condition. If your post condition is, if you compute the strongest post condition by propagated, if your actual post condition is weaker, okay, then you just have to prove that you can use the strong. Okay, what it is saying is once you generate the strongest post condition at the exit point, you can use it to prove any post condition that is possibly weaker than the strongest post condition. Yes.
Yeah.
Okay. That's what this thing is saying. Yeah. It is stating in a logical way. And similarly, if you compute the weakest precondition, then you can you can use it to prove any precondition that is stronger than the weakest precondition. Okay, so that's what this thing is saying. Yeah, here you're strengthening the weakest precondition uh, that you have calculated. Here you're weakening in the forward direction. Yeah, so those are the two things. Yeah, and that's what is the basis that allows you to use this propagation. Of course, you don't need to, and this is not the only way you could prove. I mean, this is one systematic way of proving things for straight line programs. You can either do it in a directed way. Of course, if you so choose to do it, you can insert intermediate assertions at any point, okay? And then do use forward direction propagation for some part of your straight line program and the backward direction for for that thing. You can mix and match. But usually the one way of automatically implementing these things is to do it either start with the precondition and then propagate it all the way to the exit, or do it in the backward way. Okay, that's what thing is. And SSA notation is based on forward propagation, okay, deriving the entire behavior of the program, a model for that, using the concept of strong, forward propagation. Okay, these are some examples that I will let you do. I mean, how you could instantiate and then get a proof using those rules. You can study that. This we have already gone through. Okay, so one way of using the notion of strongest post condition, and then this basically SSA notation encoding does the forward propagation by using time-stamped variables and uses the version of the forward assignment rule without by eliminating the existential quantifier using these time-stamped variables. Okay. Now, the way you remember that in the SSA notation, how do you deal with if conditional statements? We already saw informally, and this is the rule that forms the basis for doing it. If you're able to prove, so Q and S are the programs in the then and else arm. Okay, so Q is executed when B is true. So if you know that if you start in a state in which P is true, the precondition P, and in B, the Boolean thing happens to be true, and then you execute Q, suppose R is true. Similarly, if S is such that P and not B, if P and not B is true in the precondition, and then R is true in the postcondition, then you can conclude that if you start with P and execute this, if B, then Q, else S, then R would be true. Because, that's obvious because you know that the meaning of if then else is Q is executed if B is true, and S is executed when not B is true. And since in both cases you end up getting the post condition R, so you can put them together in this way, and that's how in the SSA notation we pushed the precondition across if then else. First you push P and B across Q, and then you push P and not B across S, and then you construct the combined strongest post condition. So this Another way of stating this that makes the calculation easier is this way. Okay, that if you know how to calculate the strongest post condition for Q under the condition P and B, and the strongest post condition for S under the precondition P and not B, then you'll be able to put together the strongest post condition for this construct if B then Q and S, which is what was used here, okay, where you merge, you compute the strongest post condition in terms of ghost variable on the then arm and else arm separately, and then you merge them into a in terms of if then else, okay, and that's was the idea that was used in SSA. Okay, any questions so far? Okay, so we're already at 7:07. I'll take another 10 minutes. I don't think I'll be able to complete handling the loops. Okay, how do you so far, with these things, you're able to, we are able to verify straight line programs, correct? Okay. So there are no loops here. So if you had straight line programs, then you can propagate backwards or forwards, and then you'll be able to do. I mean, you can use SSA notation as a crutch for doing the forward propagation. And so how do you handle loops? One way is you can unwind the loops to construct straight line programs and apply existing rules. Okay. But obviously there is a drawback here. I mean, you can only, loops could be unbounded, right? If your loops are bounded, like for loops, sometimes for loops are bounded, then you can use it to unwind, convert them into a straight line program, and then say apply this one. Okay, if you're using forward propagation, you can convert them into SSA and do it, or use backward propagation. Because this is incomplete with unwinding depth is unbounded, it's inadequate. It does not scale for large unwinding depths, but it still might be useful in practice as a effective debugging aid. And a lot of tools do support it in this fashion, in this incomplete fashion, that allow you to unwind all the loops in your program for up to a certain depth of your choice, and then apply the other rules like in the form of SSA, and then check the assertions. But what I want to, and even when it is incomplete, even that method is incomplete, it is useful because at least it gives you an idea. It guarantees that your program is error-free up to a certain unwinding depth. Okay, but here what we want is we are looking for something where you could verify these programs either without unwinding, or when you cannot unwind. So here, what HoareLogic uses is a concept of inductive invariant or loop invariant. So this is a way in which you could decompose the verification of a program that has loops into a just a finite number of steps rather than doing unwinding without unwinding. So what is a loop invariant? So it's a condition, a predicate Li inside a loop is inductive if it is true for all iterations. Okay, predicate that is inductive is what is called the loop invariant. That is true for all iterations. That is, if Li, and if you start with that in a state in which Li is true, and the loop entry condition LC is true, and if you execute the body of the loop, Li must still continue to be true. So it is some kind of a predicate that is preserved over all iterations of the body, okay, of the loop body. And if it is also true the first time you get to the entry of the loop, then it is called the loop invariant. Okay, any predicate that is true for every iteration, then it is called inductive. Otherwise, I mean, if it is also true for the first time you enter, then together such a predicate is called a loop invariant. The other condition is if the loop invariant is strong enough, once you exit, if it is true at the entry of the loop, and then if you exit the loop, then it must be then you must be able to prove the post condition. With all in these three, it is said to be loop invariant is said to be safe, or it is adequate to prove the property P if this condition holds good. Such, if you have that, then you see you can prove it without actually unwinding. I'll show this example and in my lecture today, and then discuss details in my next class. Consider the program here. So here there is a pre-code. You do some initialization for X and I. And then in the loop, you are incrementing X by 2 a certain number of times until in this case, 10 times, okay? And you exit the loop when I becomes, and every time in the loop, you increment I, and you exit when I is no longer is greater than, it's equal to 10, okay? So, and what you wish to prove is, after exiting the loop, is that X is even. Now, so here, a candidate loop invariant is even of X. See, even of X is a loop invariant here. Why? Because X is even the first time you enter. See, when see, you look at the way where I positioned this loop invariant. It is just at the point before you check the loop condition. Okay. So, yeah, is there a question? Oh. Uh, yeah. Sorry, I didn't see the this thing. Well, Bijayan, I think Avik has answered it, but there is an important difference. It is sequent. See, sequent calculus is rules for proving statements within propositional logic. Okay. You see, propositional logic, you can construct proofs for proving tautologies in propositional logic, and the sequent calculus allows you to do that. Okay. Now here it is for programs. Okay. The important thing is it is for programs. It's not just, of course, the sequent calculus like thing is part of the thing. But here the important thing is it is stating how to prove that a Hoare triple holds for a program. Okay, that's what it is. Huh? So that's why it is kind of an extension. It is more than just the sequent calculus. Sequent calculus applies only for proposition logic. Here, your formula, which is the Hoare triple, not only has propositional logic or even bigger logic, as the logic used for defining the pre and post, but it has a program component. Okay, so it is a logic for proving or triples. You could view it that way. So in that sense, this thing. Okay, let me get into it. Yeah. So if even of X, see, after you exit the loop, you want to prove even if x. See, it seemed like a trick, okay? So what it's saying is, if you're able to, see in this case, even if x is a good candidate for considering as a loop invariant, because the first time you come to this point of entering the loop, x is even because x is initialized to 0. And if you start from a state in which x is even and you enter the loop body, that is, I is not equal to 10, and you execute the loop body since you're incrementing x by 2, even x continues to be even. Therefore, even if x is true. So it is inductive. It satisfies the second bullet. And yeah, so it is inductive, correct? Even if you start with even of x and you execute the body, then it is still even of x. Now, and it is also the case that if x is even, when you exit the loop, that is when I is equal to 10, I is equal to 10, it continues to be true, and therefore you can conclude when you exit the loop, even if x is true. So if you can find such a loop invariant that is inductive, it is true when it is when you enter the loop the first time, and it is safe, that is when you exit the loop, it implies the post condition, then your verification of a program with loop can simply be reduced into proving 3 loop-free segments. Okay. The first part is called the initiation check. You have to prove that if after you execute the pre-code, the code that is before, that appears before the loop, if starting from the entry point of the program, the loop invariant is true. In this case, this is the pre-code. Of course, there is I also, but I doesn't affect X. And then you have to prove the inductive check, okay? This, which is the most important thing, that if you start from an arbitrary state in which the loop invariant is true, in this case, it's even if X, and you go and the loop condition is true, then you execute the loop even if X is true. So once you prove that it is inductive, then it means no matter how many times you iterate through the loop, even if X continues to hold. And then you can separately prove that if the loop invariant is true and you exit, if the loop exit condition becomes true, sorry, this should be I is equal to 10. Okay, there's a mistake here. I is equal to 10, then it is even if X, which is trivially true in this case. So this is the idea, okay, that is introduced by this rule for iteration in Hoare logic. That is, if you want to prove that starting with P, if starting with P, what you do, so if you're able to prove, if you are able to come up with the loop invariant P, which is a loop invariant for the body, which is preserved by the body. That is, if you start with that P and loop entry condition B is true, and then after executing Q of P is true, then you can conclude that if you start in a state in which P is true, no matter how many times you execute, if you exit the loop, then P and not B will be true. Okay, which this is the basis for splitting this into these 3 conditions. Now, how you come up with this loop invariant is a challenging thing. Okay, we will in the next class through examples. I'll give you some intuition. I mean, I'll give you what are the kinds of properties, what are the kinds of conditions that loop invariant ought to satisfy, and give some guidelines as to how one can come up with good candidates for a loop invariant for programs. Okay. Now, the reason I want to go slow on this and then make sure that you understand this concept of loop invariant is, firstly, this loops programming, in program verification, loops are the real challenge. Okay, it still continues to be the challenge. The question is, if you want to handle loop in a complete way, there's no other way to do it other than discovering these invariants. Okay, and proposing the right kind of invariant is a very challenging task. And a lot of people have used, of late, used machine learning techniques to synthesize loop invariants for programs. Okay, that is one of the subject matters that we will be studying in some of the papers. Okay, later on in the course, and that's why I insist again that it's important for you to understand what loop invariants are, how they're used to verify programs, and how one can construct loop invariants for various programs. Okay, so I will continue with this thing for next in the next class as well. Yeah. Okay, so any questions you have? This is a good time to stop, unless you have any questions about what I said about this program and the loop invariant. Any questions, class? Okay. If there are no questions, then I'll see you next time. So there will be a tutorial on Friday that will mostly cover Z3 related issues, including, most importantly, the Python API interface to Z3, which you need to understand, and then figure out how to use and program to solve the DNN verification problem in the class. In addition to the API, any doubts and questions you have regarding propositional logic, first order predicate logic, and other stuff using predicates to define sets of states like we're doing in pre and post condition, and Z3 related issues to solve the assignment 0, anything you can ask. And Shauryam and Avik will be available to you to clarify your doubts. And you're always welcome to send me an email and then set up an appointment to directly get the clarification from me. Okay, but that is the Z3 is the topic of tutorial on Friday. Shauryam will work with you to set up a slot, for you to attend it physically at CMI. Okay, thank you.
Thank you. So is the time fixed for the tutorial?
No, I don't think it is fixed. I don't know.
Okay.
Avik is here. Maybe Avik can answer that question.
It's not fixed yet.
Yeah, because it's already
Okay.
Wednesday. You should. I had sent a message to Shauryam. So, Avi, can you coordinate with Shauryam and the class to fix it and then conduct it?
Yeah.
Okay.
Yeah.
Yeah. Okay. Thank you.